Okay, let's unpack this deep dive. Today, we are taking on, well, one of the most intellectually demanding fields in software development, computational geometry.
It really is.
I mean, if you're building anything related to CAD, mapping, physics engines, or chip design, you know that a tiny, tiny error in a vector calculation can become a catastrophe down the line.
A complete catastrophe.
So the sources we've gathered, they zero in on a methodology called property-based testing, or PBT, which fundamentally changes how we verify correctness.
It does.
Our mission in this deep dive is to show you why PBT isn't just better testing, it's a profound leap in mathematical rigor.
It absolutely is. And the central shift we are discussing is this. Traditional testing verifies examples.
Right, just specific examples.
But property-based testing verifies universal laws.
That's a huge difference.
Think about the typical, the example-based unit test. You write a function for vector addition, and you manually select one input, say vector A1, 2, and vector B3, 4.
And you assert that the result is 4, 6.
Exactly. The test passes, and you get that little green light.
And you feel good about yourself. You've tested it.
You do. But that confidence is often misplaced. That's the core flaw of traditional testing. It creates a false sense of security.
Because you've only checked one thing.
You've only checked one outcome you anticipated for one manually selected input. You've basically verified one dot on a geometric plane that stretches to infinity.
I can visualize the problem. If you miss a subtle mathematical flaw or some edge case, maybe a weird combination of very large and very small vectors that triggers a floating point error, your unit test will just sail right past it.
Exactly. Those unit tests struggle to explore the truly vast, multidimensional input space where the most dangerous subtle bugs hide.
So with that vector addition example again.
Let's take that. Your basic test passes fine, but maybe your code includes some dependency that affects how cross products are calculated, and that flaw only shows up when one vector's magnitude is near the machine limit.
Your traditional tests will never find that.
They don't have the breadth to find it. PBT is designed specifically to hunt down those invisible flaws.
So if traditional testing relies on us, the developers, to anticipate the problems, PBT essentially inverts the model. How does it manage to verify the universal law instead of just the single example?
It's a complete philosophical shift. Instead of checking specific pieces of data, we define and test the properties that govern the data universally.
Okay.
And the process itself is highly structured, usually managed by a framework like Hypothesis in Python. There are 4 critical steps.
4 steps. Let's walk through them.
The first step is the intellectual leap. You define a property. This means formally stating a truth that must always hold true, regardless of the values involved.
So you're not testing an output value.
No, you're testing an invariant, a rule.
Give us the simplest example of a universal invariant for geometry.
We can go back to basic algebra, commutativity of addition. For any two vectors, v1 and v2, the result of v1 plus v2 must equal v2 plus v1.
It has to.
That is a foundational law of vector math. If your software violates that law, everything built on top of it will eventually fail in, well, spectacular ways. That commutative property is what you encode as your test.
Okay, so once that law is defined, how do we move beyond our one single example input?
That brings us to the second step. Generate inputs. The PBT framework takes over. It doesn't rely on you to provide a list of test cases.
It does it itself.
It intelligently and strategically generates hundreds, thousands, or even tens of thousands of random but mathematically valid inputs.
I have to pause here because that intelligently random part is crucial.
Oh, absolutely.
If I just feed truly random floats into a function that calculates polygon intersections, I'll end up with garbage inputs that aren't even mathematically legal polygons.
The test will fail for the wrong reason.
Precisely.
Precisely. The input generation isn't just chaotic noise.
So it's structured.
It uses strategies designed to cover the extremes of the input space.
Yeah.
Negative numbers, 0. Very large numbers, very small numbers, and often, critically, edge cases like degenerate inputs.
Like things that are almost 0 or almost collinear.
Yes, but those inputs must still be valid for the domain you are testing.
Okay, so that's generation. What's step 3?
Step 3 is where the action happens. The framework verifies the property. It automatically runs the test for every single generated input, and it actively hunts for the one thing that will break your assumption. A single counterexample that violates that universal property.
This sounds like a guarantee that eventually you will find a massive, sprawling, complex input that causes a failure. Which is great, you found the bug, but now you have to debug the monster input that broke it.
I see where you're going.
Say you're dealing with a 20-sided polygon with vertices defined by some truly bizarre floating point coordinates. That sounds like a complete nightmare to trace.
It would be. And that's why the fourth and arguably most impressive feature of PBT frameworks is shrinking.
Shrinking.
Yes. This is what makes PBT practical in complex domains. When the framework finds a failure, that 20-sided monster polygon that broke the commutativity of addition, it doesn't just hand you the complex input.
It does something else first.
It automatically runs a sophisticated reduction process. It simplifies the complex failing input down step by step to the smallest possible counterexample.
So that nightmarish 20-sided shape might be reduced to a simple degenerate line segment, or maybe a triangle where 2 points are almost coincident.
Exactly that. The bug that required a massive 20-sided input to manifest is reduced to the minimal input necessary to reproduce the error.
That must make debugging exponentially faster.
Oh, it does. It makes it exponentially faster and easier because you are looking at the core minimal case, not the sprawling input that happened to reveal it. That feature is the bridge between theoretical rigor and real-world engineering efficiency.
That makes perfect sense. Now, to see the true breadth of this approach, our sources weren't just focused on one type of geometric problem.
No, they weren't.
They applied PBT to two wildly different real-world libraries, showing that this works whether you're building a physical simulation or verifying abstract mathematics.
That's right. The first library was PhysPy. This operates in the well-understood domain of physical design and Euclidean geometry.
So standard stuff.
We're talking about standard, tangible, geometric operations, vector math, transformations, polygon containment, the bedrock of CAD and physical chip design.
And the goal there was pure correctness for common engineering algorithms.
Exactly. Then the second project was ProjGeoMPy,
And this one is different.
a far more abstract domain delving into non-Euclidean geometry, specifically projective, elliptic, and hyperbolic geometries. Here, you're dealing with abstract mathematical concepts like duality, perspectivity, and points at infinity.
So the goal was different too.
Right. The purpose of PBT in this context wasn't just to catch coding errors, but to verify that the code correctly implements deep, complex mathematical theorems.
Let's start with the Euclidean side, PhysPy. You mentioned encoding algebraic axioms for the core Vector 2 class. Why spend time property testing something as fundamental as vector addition? I mean, it seems so simple. Doesn't everyone get addition right?
You would hope so, but as soon as you involve floating point arithmetic, boundary conditions, or, complex hardware environments, even simple addition can harbor subtle inaccuracies.
And those can compound into major errors later.
Exactly. By encoding those foundational algebraic axioms directly into PBTs, you are verifying the mathematical bedrock itself.
So we're talking about properties like commutativity of addition, which we discussed,
Right.
but also associativity of addition, making sure that if I add three vectors, v1 plus v3, gets the same result as v1 plus v2 plus v3.
The order of operations can't change the fundamental result.
And distributivity of scalar multiplication.
Making sure that k v1 plus v2 is mathematically equivalent to calculating k v1 plus k v2. If you can guarantee these three properties hold true for any random valid vector the framework throws at it,
You gain massive downstream confidence.
massive confidence in your entire vector space implementation. You know your foundation is solid.
But the integrity of that foundation really rests on having smart inputs, doesn't it? You can't test a polygon operation with a list of 5 arbitrary coordinates that accidentally cross over and self-intersect.
Exactly. This is where the work in developing custom input strategies truly pays off. The team had to invest heavily in creating domain-specific generators.
So for testing polygons,
For testing polygons, the generator had to guarantee the output was always a valid, non-self-intersecting shape before feeding it to the test function.
because if the generator created a self-intersecting polygon, the test would fail because the input itself was illegal, not because the function was wrong.
Precisely.
So you're essentially spending intellectual effort up front to constrain the problem space to things that are mathematically meaningful.
Precisely. And the same applied to simple structures like intervals. You can't just generate two random floats. You have to enforce the constraint that the lower bound must always be less than or equal to the upper bound.
So the quality of the testing depends on the quality of the generator.
High-quality PBT is defined by the quality and constraints of your input generators.
Now, when we compare the properties verified across the two libraries, the contrast is, Wow, it's fascinating.
It really is. In Euclidean space, with PhysD-Sci, we test physical intuition, like area and invariance under translation.
Which means if you move a shape, its area cannot change.
Right. That's fundamental to physics. It makes intuitive sense to anyone looking at a blueprint.
Okay, but then you shift to hyperbolic space in ProsGMPy.
And the properties become completely abstract. They verified perpendicularity as coordinate negation.
Ah.
This is testing a non-intuitive implementation where an operation called perp creates a dual object by negating the third coordinate.
And PBT could handle that just as well.
It could rigorously verify this non-physical abstract mathematical theorem just as effectively as it verified the physical law of area invariance.
That distinction between the physical and the abstract leads us to maybe the most surprising finding in these sources, which happened in that non-Euclidean library.
Yes.
It seems PBT didn't just find a bug in the code, it exposed a flaw in the developer's understanding of the math.
That's the key takeaway from the ProsGMPy case study. The team had an initial flawed assumption about perpendicularity in non-Euclidean geometry.
What was the assumption?
Well, the initial property tests were written with the strong Euclidean assumption that taking the perpendicular, the perp of a point or a line, would result in incidence.
Meaning the resulting object would pass through the original point or line?
Exactly, which is true if you're working on a flat plane. But the PBT framework kept generating counterexamples.
It just kept failing.
It threw thousands of points at the test, and a significant number violated this expected incidence property.
So if the test kept failing, that means the fundamental property the developers thought was true for their geometry wasn't true at all.
Exactly. PBT's persistent counterexamples forced a complete re-examination of the foundational texts on elliptic and hyperbolic geometries.
And what did they find?
The revelation was that the perp operation doesn't guarantee incidence in these spaces. Instead, it rigorously creates a dual object.
Okay, we need a quick clarification here because dual object and incidence sound very similar, but clearly they aren't. Can you give us an analogy to anchor that conceptual difference?
Certainly. Think about geometry on a sphere that's non-Euclidean. In Euclidean space, a flat plane, the perpendicular line to a given line will always intersect it. That's incidence.
Right, they cross.
But on a sphere, if you take a line, which is a great circle, the dual object is its pole, the exact opposite point on the sphere.
Ah, I see.
The pole is perpendicular to that great circle, but it's certainly not on the great circle.
So a point has a perpendicular line, and a line has a perpendicular point. It's a concept of mathematical correspondence, not physical intersection.
You got it. The property being tested was correct for Euclidean space, but violated in the abstract spaces. PBT didn't just find a minor arithmetic flaw, it showed the developers were trying to enforce a flat world rule in a curved world context.
And that forced them to rewrite the tests.
To verify the correct property, that perp creates the dual object, aligning the code with the rigorous mathematical truth of that specific geometry.
It's fascinating. PDT effectively debugged the developer's mathematical foundation before it debugged the code itself. So after all this effort, what did the teams gain in concrete, measurable terms?
The increase in rigor and coverage was substantial. I mean, look at the numbers for ProsGMPy. They started with 31 tests total. That's unit tests and doc examples.
31.
After implementing PBT, they added 92 new property-based tests, bringing the total to 123. That is a four-fold increase in testing volume.
And it's targeting areas of the input space that humans never would have manually anticipated.
Never. And on the Euclidean side, where the math is better known, the results were equally impressive.
What did they see?
For PhysD-Spy, they added a total of 130-plus new test methods, all focusing on verifying the core properties of geometric primitives.
So now, every time they run their test suite, they are quickly checking fundamental invariance across a near infinite range of inputs.
That's right.
Clearly, this methodology catches bugs, but for engineers considering adopting PBT, the value goes far beyond just bug detection. What does this approach buy you strategically?
The first and most immediate return is mathematical rigor and confidence. If your software is used for critical downstream applications, science, engineering, medical imaging, you need more than a 99% guarantee of correctness.
You need to be sure.
PBT provides a depth of confidence that allows you to trust the output implicitly.
And secondly, the properties themselves become something incredibly valuable, an executable specification.
Explain that.
The properties are not just tests, they are precise, unambiguous documentation. They describe not just what an operation does, like it adds two vectors, but what mathematical laws it must obey.
That it must be commutative. It's a guaranteed contract written in code,
Which leads directly to the third strategic benefit.
which is proactive regression prevention. Once you've encoded these universal laws, they are permanent sentinels.
They stand guard.
They do. If a junior developer, or even a clever optimization algorithm, tries to refactor a core function 5 years from now and inadvertently violates one of those fundamental invariants, say, compromising associativity for a performance gain, PBT will immediately catch it. It acts as a permanent, automated safety net.
That sounds like an essential feature for maintaining large, complex code bases over time. So, if we're speaking to developers who are now convinced, what are the key practical lessons for implementing this successfully?
The experience from these two projects crystallized 4 critical success factors. First, start with the fundamentals.
Don't bite off more than you can chew.
Exactly. Don't try to test the most complex algorithm on day one. Begin by encoding the simplest, most universal properties: commutativity, associativity, basic identity rules. This gives you quick wins and builds a reliable, testable foundation.
Okay, that's one.
Second, encode domain constraints. We talked about this, but it bears repeating.
Yeah.
Invest time in custom input generators.
To avoid wasting time on invalid inputs.
Right. A test suite that is constantly generating self-intersecting polygons or illegal intervals is inefficient. Focus your testing power on the legal problem space to ensure meaningful results.
So you're not using PBT as a replacement for all your previous work.
Absolutely not. And that's the third lesson. Combined with traditional tests, PBT is a complement, not a substitute.
So you keep your unit tests.
You continue using unit tests for verifying known, specific edge cases, performance benchmarks, and explicit API contracts. You use PBT for verifying universal invariants across the vast, unknown input space.
And the final lesson.
The final lesson, which connects back to that non-Euclidean revelation, is to embrace surprising failures.
Don't be afraid of the red text.
The failing property test is often the most valuable finding you will get. If it fails, it's not just a coding error. It is a critical learning opportunity that might reveal a deeper conceptual misunderstanding about the math or the physics or the logic of your problem domain.
That lesson on treating failure as revelation is great advice for any engineering discipline. And for you, the listener, if you work in a language beyond Python, know that this is a robust cross-language paradigm.
It's not just a Python thing.
Not at all. While our case studies used Python with the Hypothesis framework, this same rigor is available in powerful libraries across the industry, like RapidCheck for C++ and QuickCheck and PropTest for Rust.
So you can maintain this high mathematical consistency regardless of your stack.
Right, though you might choose C++ for superior performance or Python for ease of use.
Ultimately, adopting property-based testing is far more than a technical upgrade for your test suite. It's a forced change in design philosophy.
How so?
It moves the conversation away from the implementation details,
Yeah.
how to write the function, and forces developers to define the fundamental, immutable truths of their system.
It forces you to think like a mathematician.
In a way, yes. By taking the time to encode these universal truths as executable properties, you are building software that is not merely tested to a high degree, but is engineered to be mathematically sound by its very design.
So here is a provocative thought for you to chew on. Consider the most complex or abstract algorithm you are currently wrestling with in your field. Doesn't matter if it's geometry, concurrency, or data sorting.
Find the one foundational truth.
Find that one property that must always hold, no matter the input. Start there. What fundamental assumption could PBT force you to question about your design, and what deeper truth might it force you to reveal?